Yeah, so now that we know how to calculate the adjoint of the matrix, let's look at the inverse. And the simple way to calculate the inverse of the matrix is defined as the adjoint of the matrix divided by the determinant of the matrix, provided that the determinant is non-zero. Clearly, the inverse only exists for square matrices, and by definition A times A inverse equals I, where I is the identity matrix of order n. So let's take the same example as the previous section. So to recall, we had this matrix X as 3, 0, 2, 1, 6, 0, 0, 9, 7, and we calculated in the previous section adjoint of X as 42, 18, minus 12, minus 7, 21, 2, and 9, minus 27, 18. You can also find out the value of the determinant. So that would be expanding by the first row, 3 times 42 minus 0, minus 0. So the second term of the expansion is 0, plus 2 times simply 9, equals 144. So then, using this formula, now that we've calculated the determinant is non-zero, we can find out the inverse of matrix X, which works out to be adjoint of X divided by the determinant of X. And you can show that it works out to be 7 over 24, 1 over 8, minus 1 over 12, minus 7 over 144, 7 over 48, 1 over 72, 1 over 16, minus 3 over 16, and finally 1 over 8. So that is the way to calculate the inverse of the matrix. So now we need to look at some properties of the inverse. Let's take a different color. So let's say you're able to find out the inverse of a matrix A such that B equals A inverse. Now, does B have an inverse? Well, yes, and the answer is obvious. B inverse turns out to be A again. Then if you multiply a matrix by its inverse, then this is by definition the identity matrix, which is also A inverse times A. Then if you want to multiply it by a scalar, so K times A, and if you take its inverse, equals K inverse times A inverse, provided K not equals 0. If you have the product of two matrices, so AB inverse is B inverse times A inverse. So the order is flipped. And for the more general case, if you have many such matrices, A1, A2, all the way through AP inverse, then in the inverse form the order is reversed. So it will become AP inverse times AP minus 1 inverse all the way to A1 inverse. And then if you take the inverse of the transpose, that is the same as taking the transpose of the inverse. So inverse and transpose, these two operations are invertible, so to speak. Now if you have a diagonal matrix, so if A is a diagonal matrix, which basically means only the diagonal elements are non-zero, let's say C1, C2, Cn, all the non-diagonal elements are 0, then A inverse is a diagonal matrix again, which consists of 1 over C1, 1 over C2, all the way to 1 over Cn, provided Ci not equals 0 for all I. So this is one definition of how to calculate the inverse of a matrix, and here's an alternate definition. So we can write a matrix A as I times A. I is simply the identity matrix, so pre-multiplying a matrix by itself gives the same matrix as the original. If you can do a series of row or column transformations on the matrix to get it such that it changes to this form. So from A equals I times A, you can change it to this form, I equals B times A. Then this implies B equals A inverse, because only A inverse times A can give you the identity matrix. So this is by a series of row or column transformations. So with all this background, we are now fully equipped to study how to solve a system of linear equations, simultaneous linear equations in n unknowns, using either matrices or determinants. And this is the most important part of the chapter, which shows a direct practical application of what we have studied so far. So simultaneous linear equations. So let's consider a general set of n equations in n unknowns. So we can write it as a11 times x1 plus a12 times x2 plus a1n times xn equals b1 for some constant b1. The second equation can be a21 times x1 plus a22 times x2 all the way to a2n times xn is b2. And you can keep writing this all the way to an1 times x1 plus an2 times x2 ann times xn equals bn. So this is a set of n equations in n variables, x1, x2 all the way to xn. And let's say our job is to find the values of these variables which satisfy this set of equations. Now, as you can already see by the way it's written, an easier way to represent this information would be in matrix form. So this brings us back to the original idea of a matrix, why it is so useful as a method to represent large amounts of data, all the way to A1n, A21, 22, 2n, and similarly n1, n2, nn times the variables x1, x2, xn. So this is the product of the prefactors or the coefficients of these variables times the number of unknowns, and your right hand side is the constants in the equation. Or even more compactly, we can write this as A x equals b, where A is this matrix, x is this matrix, and b is this matrix. Now, before we look into how to solve this system of equations, there are two types to consider. So one is the special case where each and every element of the right hand side is 0. So b1 equals b2 all the way through bn equals 0. Then it is called a homogeneous set of equations. And if at least one of b1, b2, bn is non-zero, the set of equations is called non-homogeneous. And we will look at this general case first.